Should I? Yeah. Whether I'm audible
Yes, sir. Yes, sir.
and PPT is visible. No?
Yes, sir. PPT is visible.
So today we are going to discuss the some more concept of the IIR filters. Here we will try to discuss the roles of the filters and then the two concepts of the IIR filter, that is the bicard structure and the direct form implementation. We will also discuss the stability and the role of the Z and Laplace transform during the time of the designing of the IIR filter, and we will also discuss here the cascading of the biquards for the digital as well as the analog filters here. So we are just going to describe here the roles for the filters. When we say the filter is nothing but it selects the some ranges of the frequency and discards the unwanted ranges of the frequency, or we can say it is system that operates on the signal in order to extract the required information here. So when we say the concept of the noise removal, it means the signal and noise spectrally has to be separated here. And for example, if we consider here the band pass filtering to suppress out some noises here, then we are just selecting the range of those frequencies have been selected between the lower cutoff frequency to the higher cutoff frequency. Otherwise, the other ranges of the signals will be discarded here. And we will also try to discuss the analysis, synthesis, and compression here in these concepts here. And then we will also discuss here the what is the spectral shaping, how the shaping will take place here. And we have also discussed in the previous lectures these concepts here. Now, if we use here the digital IIR filter, then in the digital IIR filter, we can say infinite impulse response filter, and that has the impulse response for the infinite duration. For example, if we consider the HN, that is the here the impulse response, it is the 1 by 2 to power n, and un, that is the, if we multiply this one by the un, it means now the signal is causal, but at the same time it is 1 by 2 its power n. N is nothing but that is the discretized time domain here, and it exists for any values of the n. It means for the infinite range. When we will transfer this information time domain to the z domain, applying the z transform, then we will get here the 1 by 2 to power n z to power minus 1 with the summation series starting from 0 to infinite. Or we can say this may, after some manipulation, this can be represented something like in this manner, that is the 1 by 2 z power minus 1, its total power of the n, and the range of the summation is n is equal to 0 to infinite. It means it is for the infinite duration. That's why whatever is the impulse response that will exist for the infinite duration, and we call it the infinite impulse response filter here. How to implement the IIR filter? By the using the software concept here, that is using some packages or using some computer concepts here. Now suppose we consider any input signal, that is the x of the k, and corresponding output is the y of the k, then naturally the system function will be described as the Z transformation of the output, ratio of the Z transformation of the output to the Z transform of the input, with all initial conditions considered to be 0 here. So, and if here the yz is given, say this is the 1 upon 1 minus 1 by 2 z to power minus of the k, this will be multiplied by the xz here. Then yn will be represented in time domain something like in this manner, that is the yn minus 1 by 2 yn minus 1, and this is equal to the xn. And after some manipulation, that is the yz is the multiplication of the sz and xz, and hence we can again write here the yz in this form. We can say the yn is 1 by 2 yn minus 1 plus x of the n. Again, here we can say this yn, by which we can compute the n yn, and when we consider the n greater than or equal to 0, that is the n is positive, it exists for the infinite duration here. And the nature of this one is whatever is the output, that will be again considered into the input. It has the recursive nature, so the recursively we have to compute the output. Different FIR filter representation. As we know, if we consider any filters, the coefficients are given as the 1/2 for the first delay and 1/8 for the second delay, and the xn is the present here the, and yn is represented as the 1/2 yn minus 1 plus 1/8 yn minus 2 plus xn. Then recursive computation needs here the initial values of the, because when we consider the n is equal to 0, it needs y of the minus 1 and y of the minus 2. And if we consider here the y of minus 1 and minus y2 is given 0, and it is here the condition when we consider the LTI filter. At that, with these conditions, we can compute here the yz. How the yz will be completed? Yz is the z transformation of this one, and after computing the yz, how we can calculate the transfer function? Again, it will be the z is yz upon the xz, and given by this one here. Means the poles are lying at the minus 0.183 and 0.683 here. And if we see the structure of this one, then yn is nothing but this is the 1/2 yn minus 1. That is the yn is delayed by 1 unit, then this will be multiplied by 1/2. And the next term is the yn is delayed by 2 delays, that is the again delayed by 1 unit. So we will get here the yn minus 2, and it is multiplied by 1/8. And hence by taking the summation of these two outcomes here, and along with the input xn, we will get here the yn. This is the structure of this algorithm that we have discussed in order to describe the IIR filter here. Now, if we see the order of this filter, then since there are the two bit energy storing capacity, or we can say there are the two delays, so we can say this is the second order system, and having the two poles and the no zeros, that is the zeros here. Now, if we consider this one is the discrete time IIR biquad having the numerator and the denominator, then this may be represented something like in this manner, that is whatever is the in here the unit signal that is delayed by 1 unit, and then it has been multiplied by the A1 and B1, and again delayed by the 2 and multiplied by A2 and B2. We have described this biquad section during the time of the direct form and the direct form 2 realization of the FIR filter here. And we will get here the HZ, that is the system function or the transfer function of the this biquad, that is the Z transform of ratio of the Z transform of the output to the Z transform of the input with all initial conditions considered to be 0, and this will become the V0 plus B1 Z power minus 1 plus B2 Z power minus 2, and 1 minus A1 Z power minus 1, 8 minus A2 Z power minus 2. And we know, which we have discussed already in the previous classes, that if this is the structure, then we will consider here the coefficients, left side's coefficient will be considered negative and right side coefficients will be considered as the positive here, since these are the coefficients here, and numerator is written as the B0 plus B1 Z power minus 1 plus B2 Z power minus 2, and similarly this one will be written as 1 minus then multiplied by the first coefficient Z power minus 1 minus A2 Z power minus 2, and so on. Now, this is the two poles and two zeros. So now, if we consider here the biquad during the time of the designing or during the time of the implementation of the IIR filter, when there are higher order filters, coefficients are more sensitive to the parametric to avoid these type of the sensitivity, which are the unwanted sensitivity. We have to consider the first order section as well as the second order section here. Now, discrete time IIR filter design. If we are in order to design any system and say Hz is given, and this is the Hz, that is the transfer function, as we have derived the transfer function, and after getting the transfer function, as say this is the here function where the c is any constant, and now if we replace the z by e to power j omega, then finally we can write this h e to power minus e to power j omega, something like in this manner, and after some manipulation finally we can write this one in this form here. As we know, if we consider a mod of the a minus b is a distance between the complex numbers a and b, for the at the p naught, this one here, and this will be the transfer function here. And when poles and zeros are separated in angle, then what happens? Poles near unit circle gets
Sir, sir, voice is not clear.
Okay. And what about the PPT? It is clear?
PPT is okay. Yes, sir. PPT is visible and it's okay.
Okay. So, and voice?
So now it's okay.
So I think there is some network. Better, yeah, please. And this is a if you consider the vectors a and b, a minus b its mod is a distance between the complex numbers a and b. Similarly, if we see here the denominator, then we'll find these denominators are written at e to power j omega minus p naught and e to power j omega minus p1. These are the two poles here. Similarly, in the denominator are the two zeros and these are not z1. And we have to see that if we consider e to power j omega minus p naught, then what is the meaning of this one? It is nothing but it locates a distance from the unit circle to the location of the poles, that is the p naught here. And if we have located the poles, and then in circle indicate are nearer circle, they indicate the filter's pass band or the pass bands here. It is indicate the pass band here. And if the zeros are near unit circle, then they will indicate the stop band or the stop bands here. So accordingly, we can decide what is the type of the filter here, whether that is the passband type or the stop band type here. And now, say if we consider any transfer function hz, that is represented as the c z minus z naught multiplied by z minus z1 upon z minus p naught z minus p1, and and written something like this manner: 1 minus z naught z1 minus 1 and 1 minus p1 z here. Now poles are conjugate symmetric when transfer function coefficients are real valued. Then what is the meaning of this one? It means poles are conjugate symmetric are the real value, or vice versa is also true. If the coefficients are, presently we are in class, wait, poles x are conjugate symmetric are the real value, and if similarly the zeros are conjugate symmetric are the real value, then what will happen? Real value, then we can say the poles are conjugate symmetric are the real value, and if the zeros are conjugate symmetric are the real value, both conditions are satisfied, then at that time we can say what is the meaning is the real value coefficients here. Filters below have what magnitude responses. You have to find the response magnitude of these filters here. As we have described, कौन वेट कर रहे हैं? अजय से कहो मिले, क्लास है अभी बाद में मिले. तो अब स्टूडेंट है तो वेट करें, क्लास के बाद मिले, नेट चलने लगा. Zeros are here, the zeros are on the unit circle, and the real as we have described in this one here, how we have to calculate the distances between the two numbers a and b. We can say these are the three location and positions of the zeros and poles of filters, and we have to calculate the magnitude of these filters here. So it is the assignment for you that for these three conditions for which the location and positions of the poles and zeros are given, you have to calculate what is the magnitude response of this filter, and then you have to apply with respect to the frequency here. Now if we consider a direct form IIR filter realization, the Hz is given, as we know, Hz is function yz upon the Pz, and this is given as the here the Z transformation of the here the numerator to the Z transformation of the denominator, and it is written as power minus 1 to the amz power minus m here. And this can also be written something like in this manner, that is the yz multiplied by 1 summation of the amz power minus m, with m starting from 1 to the m, and it will be x multiplied by the k0 to n bkz power minus of the k. Now the direct form realization, here the dot product of the vector of the n plus vector of the current input and various n input FIR sections here. See here, this is represented in this one here. The dot product of the vector of the n plus 1 coefficients and vector of the current input and previous n input. If only this section exists, then what happens? It is only the FIR section here. And dot product of the vector of the m coefficients and vectors of the previous m outputs. FIR filtering the previous output values are taking place. That is the second one is alpha is the part here. It means the FIR filtering of the previous output values are taking place here. Now the computation, there are the two terms. What is the computational complexity? The total computational complexity requires the m plus n plus 1 multiply and accumulate. That is the max of this. So what is the computational complexity of this equation or this algorithm? That is the m plus 1 plus n plus 1 computational accumulates multiply accumulates. That is the max operation here, and the memory that is required m plus 1 word for previous inputs and outputs, and m plus n plus 1 words for the coefficients here. So during the time of the implementation, if we are interested in order to calculate the complexity, or we are interested to calculate the cost of any filter, then on the basis of these computational complexity, we can calculate the cost of the filters here. One more thing that has to be added here, during the time of the realization, or during the time of the presentation of the filters, we have discussed that any filter or any system's algorithm can be represented using the some any one of the and we have discussed that there are the so many types of the graphical representation. One is the block diagram, one is the dependence graph here. And we have discussed that block diagram describes the architecture of the signal flow graph, gives the information about the flow of the signal flow graph, that is the DFG. It describes the what this graph describes the complete here. Now suppose we have realized any filter after deriving the HZ, that is the transfer function. Suppose we have realized any filter here, then we have to compute the computational complexity in order to know what will be the cost of this system, which has to be designed before implementation. System. So for that we have to compute the computational complexity, and that will depend upon the MAC operation, that is the multiply and accumulate operation, and what are the number of the addition multiplications, as well as the memory required here. Now, if the system is very costly here, or we can say there is a need of to settle the trade-off between the cost and the performance, then for that purpose another type of the algorithms are applied here, as we have discussed that using the DFG, that is the data flow graph, we can demonstrate here one iteration of any algorithm. So with the help of the DFG, we now we can reduce the computational cost here by using the pipelining and parallel concept, and we can also introduce here the timing, retiming, folding, unfolding types of the algorithms in order to reduce the number of the additions, multiplications, and the memory devices here. So there are the so many algorithms that can be introduced in order to change the realization of the design filter here, but try to maintain the same performance here, and that is known as the modified enhanced algorithm here. Now, if we see here the filter structure as a block diagram, as we know, we have discussed that from the direct equation we can draw the block diagram here. But after some manipulation, because this one is the feed forward concept and this is the feedback concept, here we are just introducing some concept in order to reduce the complexity. And how the complexity is reducing? By taking the by interchanging the location and position of the two subsystems here. We can say feed forward is the H1S, and this is the H1Z, and this is the H2Z here. Now we can change the location and position of these two transfer functions, and then what will happen? The unit delay branches will merge with each other, and hence we can get here the lower number of the or lesser number of the memory devices, and hence we can say we have reduced the complexity, or we can say we have reduced the area on the silicon wafer that has to be implemented here, and that will be very beneficial during the time of the implementation using the VLSI concept here. Or we can say also now the memory space will be lesser during the time of the implementation. So whatever is the designing that of the system, the design system has to be implemented using the software approach or the hardware approach. And in both the cases, we will try to reduce the area, or we can say we will also try to reduce the computational complexity. We have also discussed that in order to analyze the performance of any designed and implemented system, uh, we have to consider at least the 4 parameters, and these parameters are: the first one is the delay, means what is the propagation delay related to a particular algorithm, or we can say what is the speed of the algorithm. And the second one is the power consumption, that is in order to implement the algorithm, what is the power required, energy consumption that is required for the purpose of the implementation. And the third one is the here we can say third is the what is the area that is related to the computational complexity here. And the fourth parameter is related with the concept that is related to the finite precision here, because during the time of the implementation we have to consider the finite word length, but we have during the time of the designing we have considered the infinite precision here. So when we consider the finite precision, at that time there will be the here the lesser number of the word length. So what will happen? Now the quantization effect will take place, and due to this quantization, or we can say due to the truncation or the rounding, there will be the here the quantization error, and that will cause here the limit cycle oscillation and other type of the effects. So what is the effect of this quantization? It has to be also analyzed. So when we design any system, then after the designing for the purpose of the analysis, in order to analyze the performance of the system, we have to analyze at least 4 parameters. The first is the speed of the algorithm or the speed of the system. The second one is the area, and the third one is the power consumption, and the fourth one is the finite word length effect. And when we consider the finite word length effect, naturally there is a need of the rounding or the truncation, and we have to analyze the different type of the rounding and the truncation also. And in the next class we will discuss the concepts of the different type of the quantization here. Now say if we whatever we have discussed in the first slide, in previous slide here, this is the direct form architecture, and now if we apply here some concept, then we will get this one here, that is the number of the energy storing devices or the delays have been reduced here. So in this one, what is happening? The complexity is reduced. Now we will come to the a concept that is known as the stability. And in order to, suppose we have designed any system, then first we have to analyze the computational complexity, and then we will move towards the stability, whether the designed system is stable or not. As we know, the Vivo stability describes that the bounded input, if any system is subjected to the bounded input and the response is also bounded, then we can say it is a stable system, that is bounded input, bounded output, stable system here. What is the meaning of the finite input? Means if the here the magnitude or the mod of the input or the xm say is less than any finite value, and any value and that is less than the infinite, means that one is the finite, and the output is also finite, that is the mod of the yn is less or equal to a particular value v2, but v2 is certainly less than the infinite here, that is the finite value here. Then how this is possible? This is possible only due to this concept that the mod of the hn with the summation series n is equal to minus infinite to the plus infinite, it must be less than infinite, that is the it is a finite value. It can be derived from the here the convolution theorem, that the yn is a convolution of the xn and the hn, and this may be represented as the summation series n is equal to minus infinite to the plus infinite hn multiplied by xn minus k here. And if we see this one condition, then what is the meaning of this one? That is, the impulse response of the system must be absolutely summable. If the impulse response of any system is absolutely summable, only then we can say the system is a which type of the system? That is the stable system here. A causal finite impulse response LTI system is stable if and only if its poles lie inside the unit circle. If this is the condition, that is the if the absolute here the absolute summation or the it is absolutely summable, its summation is less than infinite, that is it is finite value, then system is said to be the stable. But what is the condition when this condition will exist? If here the poles are lying inside the unit circle, only then these conditions will be fulfilled here. Now, for the Vivo stability, rule 1, for a causal sequence, poles are inside the unit circle. That is, after applying the Z transform to the functions, here we will get a ratio of the two polynomials, and then we will we will see the location and positions of the poles, and if the poles are inside the unit circle, then we can say the system is stable. The rule 2, unit circle is in the region of the convergence. If the unit circle is lying in the region of the convergence, because if we are taking the Z transform and the defining Z transform without the region of convergence is meaningless. So in continuous time, imaginary axis would be the region of the convergence of the Laplace transform. Now, if we consider here the an as a causal signal, so it will be multiplied by the an un, and if we apply the Z transform, then we will get its Z transform. As we know, it becomes the 1/1 minus a Z to the power minus 1, and it is the stable only when the mod of a is less than 1, or vice versa is also true here. That suppose the question is given something like in this manner, that is what is the condition on the a, or what will be the value of the a, so that this system is stable. Or say the value of the a is given 1, 2, 3, 4, 5, 6 and 0.5, for which values this will be stable here. So accordingly we can see what is the condition for the stability of the system. Now, Z and Laplace transform. As we know, in the Laplace transform, S, there is a term parameter S that is known as the complex frequency, and this complex frequency is represented as sigma plus j omega, or the j2 pi f. Sigma is real value here, that is responsible for the damping here, and similarly Z r e to the power j omega. And the second part in this one and this one, in both the cases, these are responsible for the oscillations here. And the transform kernels are complex exponential and eigenfunctions of the linear time invariant systems here. Now, if we consider the Laplace transform e to the power minus st, it becomes e to the power minus sigma t minus e to the power minus j omega t, or we can say e to the power minus sigma t into e to the power minus j2 pi ft. Similarly, if we define the z, it can be written as r e to the power j omega, its total power minus of n, and r to the power minus n, and e to the power minus j omega n. Now, if we see this, these values which are encircled by the blue color, then these values are responsible for the damping, or we can say these are the damping factor here. And this these terms, that is the second term e to the power minus j2 pi ft in the case of the Laplace, and e to the power minus j omega n, these are the oscillation term here. So we will consider only the second one during the time of the processing of the signals here. Now we will try to describe the mapping from jet transform to the Laplace domain or Laplace to the jet transformation. Sir, class पे है sir. ठीक ठीक सर. अच्छा हाँ अंदर क्लियर है ना सर. हाँ ठीक 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 सर ठीक ठीक सर ठीक ठीक ठीक. अच्छा अच्छा सर थैंक यू सर थैंक यू. ओके ओके नमस्कार. So basically there is no proper mapping, unique mapping. During the time of the mapping, we have to make some compromise, and we have also discussed that there are the different types of the mapping which are used. And during the time of the mapping, the main point is we have to consider here the imaginary axis, and imaginary axis is the condition for the marginal stability, and now this imaginary axis is transformed to the unit circle in the Z domain, and that is the imaginary S is in the this one is transformed in the form of the unit circle here the perimeter. Next is the left side of this one. The left side of this one is region which is set to the region of the stability, and this one is transformed inside the unit circle here. So in the Laplace domain, whatever is the left hand place, that will be inside the unit circle, and imaginary axis will be transformed, it will be mapped to the unit circle. Right hand plane will be mapped to the outside of the unit circle. Now we have to describe the conditions for the low pass, high pass, band stop, all pass, and the notch filters. What will be the conditions? Now, according to the location and positions of the zeros and the poles here. And here the one example is given here in the analog as well as in the case of the digital. Again, it is a tutorial for you that you have to find what will be the type of the filter, whether it is the low pass, high pass, band stop, all pass, or the notch filter. Now, if we consider the continuous time factor, and in the second order filter sections with the two poles and the 0 to 2 zeros, means there will be the 0 zeros, 1 zeros, 2 zeros, and that will be the second order filter here. The transfer function is a ratio of the two real valued polynomial poles, and the zeros occur in the conjugate symmetric pairs here. Quality factor, as we know, what is the quality factor? The technology independent measure of the sensitivity of the pole locations to perturbation here. For an analog bicod, suppose there is a pole at suppose there are the poles which are the conjugate poles A plus JB, where the A is less than the 0, means that it is negative, then naturally the system will be the stable here. Then the quality factor is defined as the in under root A square plus B square minus of the twice of A. For the quality, and the quality factor will be between the 1/2 to the infinite here. Real poles, suppose the B is 0, so Q will become the 1/2, and that is the exponential decay response. And imaginary poles, say A is 0, then what happens? Q becomes the here the infinite, that is the oscillatory response will take place here. Now we are discussing some concept of the continuous time IIR filter. Here suppose A is less in the A plus JB is less than 0, but there are no zeros, then HT will be C e to power AT, that is the cos BT plus theta, like that one. And this will be the pure sinusoid when A is equal to 0, and pure decay when B is 0 here. Breadboard implementation, we know this concept that in order to design any filter, we have to use the RC filter. and according to the frequency, we have to select the value of the R and C. And here it is the tutorial by which we can select the values of the A and B. Now the classification of the IIR filter. We know the depending on the graphical representation, the Butterworth filter is the first category, that is the monotonically decreases in pass band and the stop band, means there is no ripple. And Chebyshev type 1 monotonically decreases in pass band but has ripples in the stop band. Chebyshev type 2 has ripples in the pass band but monotonically decreases in the stop band. Elliptic has ripples in the pass band and the stop band. We have discussed these concepts here. Analog low pass filter. Here the pass band, stop band age frequencies are given. Ripples in the pass band, ripples in the stop bands are given, and this has to be represented here. We can design this type of the filters, and we can see the here the ripples, and basically this is for the elliptic one, and then we have utilized here the optimization concept. So it is again a tutorial for you that in the laboratory you have to design the elliptic filter using the here the pass band stop pass band age frequency, stop band age frequency, and the ripples in the pass band and the stop band, and then you will try to optimize the filter. And how it will be optimized? When you will look into the FDA tool, then towards the right side there is a optimization button, and by when we will select this one, then there is a choice to optimize the filter, and according to the available choices we will select that type of the optimization and we will optimize the filter. After optimization, now what will be the difference between these two types of the design? One is the design filter and the second one is the optimized filter. And in both the cases we will also analyze the here the location and positions of the poles and zeros as well as the Q factors. One example is given here. Accordingly, you have to prepare the table and you have to write some comment on your results. Now, for that purpose, you have to use the pass band age frequency given as the 9600 and stop band age frequency 12,000. And naturally, the low pass filter has to be designed, and then sampling frequency has to be 48,000. The attenuation in the pass band 1 dB, attenuation in the stop band. A pass, that is the maximum attenuation in the pass band, and A stop, that is the minimum attenuation in the stop band. You have to design it, and then you have to write the here the comment something like in this manner. That is, you after designing see the location and position of the poles and zeros. Then from the window visualizer tool, you have to edit. You have to copy the here the location and positions of the poles and zeros figure. Copy the figure and paste it into your report here. These are the some reports which are given here. Accordingly, you have to write the report and then you have to compare here the two types of the filters, that is the FIR filter and the IIR filter. In terms of this one, that is the for the same specification, you have to write what is the complexity. Here you have not to write only the higher and lower, but you have to write the exact value of the complexity in the case of the IR, in the case of the IIR filter here. And in you have to also compare here the in which case you are getting the linear phase and whether the system is stable or not. So we have discussed here the designing concept of the IIR filter, and starting from the very basic concept, and basic purpose of this lecture was to compare the performance of the FIR filter and the IIR filter, and for that purpose you have to utilize these concepts in the laboratory for the in order to see here the different parameters, and then you have to analyze, and finally you have to conclude your experiment in such a manner that the complex for the given specification, in which case complexity is higher and what is the percentage of that one. Naturally, the complexity, in order to get the same performance, the order of the filter in the FIR must be higher than that of the IIR. It has to also be mentioned in your comparative result here. So this is about the today's session, and if you people have any doubt or any question, then please ask about it.